Hello, today we are going to talk about a very interesting topic in Fourier analysis. We are going to make use of some concepts that we have been watching in recent lessons, and we are going to recall now that the Sturm-Liouville differential equation comes from an expression like this: r of x y double prime plus r prime of x y prime plus q of x plus lambda p of x times y equals to 0. Remember that there is another condition that we need to add to this differential equation to be considered as a Sturm-Liouville problem. But we can generalize the Sturm-Liouville differential equation to another one of the form a of x of y double prime plus b of x y prime plus q of x plus lambda p of x y equals to 0. The thing here is that, well, here we have the derivative of this first function, but this b of x is not necessarily the derivative of a of x. The thing here is that we saw on a previous lesson, there is a lesson where we showed how to get to the self-adjoint form of the Sturm-Liouville problem. And we got that, well, we can express this as an equation of the form y double prime plus b of x divided by a of x y prime plus q of x divided by a of x plus lambda p of x divided by a of x times y equals to 0, such that we can find an integrand factor mu of x that if I multiply this element by this mu of x, then we are able to express all this equation as the derivative with respect to x of mu of x y prime, and then all this expression as it is. Okay? So this is known as the self-adjoint form of the Sturm-Liouville differential equation. Okay? So what we want to do today is to establish a relation between the Sturm-Liouville problem and the Bessel equation, okay, which is a very important equation in physics. It appears in many problems, and as you will see, we will be able to relate the Bessel functions with the Fourier analysis. But for now, you need to remember that, well, the very well-known Bessel equation has the form x squared y double prime plus xy prime plus x squared minus, let's say, beta squared y equals to 0. So as we did here, we can divide by x squared, which is the coefficient of the y double prime, to get y double prime plus x divided by x squared y prime plus, here it will be 1 minus beta squared divided by x squared y equals to 0. And I let this function as this because, well, you should remember that this integrand factor that we found in that video, well, it is defined as e to the integral of b of x divided by a of x dx. Recall that, well, b of x divided by a of x is this coefficient of the y double prime, right? So in the Bessel equation, that coefficient, it will be x divided by x squared, which is of course 1 divided by x. So if we want to restructure this equation into a Sturm-Liouville self-adjoint form, well, we need to multiply by this factor defined as e to the integral of, well, x divided by x squared, but that is 1 divided by x dx. And as you can see, this is going to be e to the natural log of x, which, well, plus some constant, right? But we will not be interested in that. We will take that constant to be equal to 0 to get that this will be just x, right? So after having this structure, we can multiply by x to get x y double prime plus y prime plus x minus beta squared divided by x times y equals to 0. And well, this equation can be transformed very easily to a self-adjoint form as the derivative with respect to x of xy prime plus x minus beta squared divided by x y equals to 0. Okay, so yeah, this will be like the self-adjoint form for the Bessel equation. Okay, and recall, this is the original Bessel equation, but there is another form that we find for the Bessel equation known as the parametric equation of Bessel. So that equation is only going to add a parameter that will be named as alpha squared here, right? It's just a constant, but it will change the structure of the Bessel equation such that we include this new parameter. That's why this is this is known as the Bessel parametric equation. And this is the equation that we are going to use to work. Okay, perfect. So this equation is telling us that the Bessel equation is of the form of the Sturm-Liouville problem. And you should know that, well, there are many videos in YouTube already showing how to get to the solution of the Bessel equation. So I'm not going to show how to get to the solution. I'm just going to write the formula, right? That is going to tell you what is the solution to the Bessel equation. That formula is the next. Okay, these are the solutions to the Bessel equation, right? But not are the solutions to the parametric Bessel equation, which is the one that we are going to work with. The thing here is that to get the parametric Bessel equation, we only need to multiply this by a factor of alpha squared, right? So instead of taking the x into the solution of the Bessel equation, we need to take alpha x, right? We need to switch x for alpha x. So that means that here instead of x, we will have alpha x, alpha x, alpha x, and alpha x. Right now, well, these functions that we have here represent the solutions to the parametric Bessel equation. Okay, so what is this telling us? Well, looking at, we have a Sturm-Liouville problem that has the next condition. Let's say A1 Jn alpha b plus A2 Jn, alpha Jn prime alpha b equals to 0. And we have the solutions to this problem. We saw on the first video talking about the Sturm-Liouville problem that if we find some functions that are solutions to this problem, these functions need to be orthogonal with respect to some function p of x, right? This is why it's important for you to check that first lesson. The thing here is that we are constructing a Sturm-Liouville problem from the Bessel equation and its solutions. So, for you to see it easier, we can say from this parametric equation that we have the form the derivative with respect to x of r of x y prime plus, let's say, lambda p of x plus q of x y equals to 0, right? Recall that this is the general structure of a Sturm-Liouville problem. Here we can identify p of x as x, lambda as alpha squared, q of x equals minus beta squared divided by x, and r of x equals to x. The thing here is that we showed that for this Sturm-Liouville problem, the solutions y for this differential equation are orthogonal with respect to p of x. That means that the integral with the limits on the interval of definition of the problem, let's say AB, of P of x times one solution, let's say y sub n of x, and another solution y sub m of x dx is equal to 0 if I is different from j. Okay, so this is in the case of the Sturm-Liouville problem. We are taking a general case, right? But now we are going to take the case where we take the Bessel function. So in that case, we will have that, looking at the interval of definition that I didn't mention is the closed interval 0, b. We are going to take the integral from 0 to b of p of x that we mentioned. It is this x right here. Okay, so it will be the integral from 0 to b of x of, let's say, one Bessel function of order n that is evaluated at alpha I x, and then another Bessel function of order n, but now evaluated at alpha j x, and then dx. And this is going to be equal to 0 if I is different from j. Okay, now this is the orthogonality relation for the Bessel functions. Perfect. This is the main idea that I wanted to reach. And why is this? Because we made another video talking about orthogonal functions, and we showed that if we have a set of orthogonal functions, for example in this case j and alpha I x, where I goes from 1 up to, well, it can be any natural number, right? Well, if we have this set, then we are able to express a function f of x as a linear combination of these functions, right? Like this. This is from I equals to 1 up to infinity. Okay, and this is because these functions j sub n, well, they are orthogonal. Okay, so to be able to express this function f in terms of these elements, these Bessel functions, right? Well, we need to find these constants. Okay, so we have made this process in that same lesson of orthogonality, but I'm going to recall that the process, well, is not very hard. I mean, first of all, we can express f of x equals, let's say, c1 jn alpha 1 x plus c2 gn alpha 2x plus all the way up to infinity, right? But then we will get to some element, maybe the element, let's say, cm gn of alpha m x, right? And we keep going. So what we are going to do is to multiply this equation by x times gn alpha m of x. Okay, so this is going to give us x gn alpha m of x times f of x equals, let's say, x gn alpha m of x times c1 gn alpha 1 of x plus c2 gn alpha 2 of x times gn alpha m of x plus all the way up to this element, which is going to be x cm jn alpha m of x gn alpha m of x and all the way up to infinity, right? And then with this equation that we have here, we are going to take the integral from 0 to b on both sides of the equation, right? So this is going to give us the integral from 0 to b of x f of x gn alpha m of x dx equals the integral from 0 to b of c1x jn alpha m x gn alpha 1 x dx, and then plus the integral from 0 to b c2x Gn alpha mx Gn alpha 2x dx all the way up to the m element, right? The integral from 0 to b of Cm x Jn alpha m x Jn alpha m x dx, and then plus all the way up to infinity. The thing here is that we have constructed the inner product of, well, every function of Bessel with the particular function Jn of alpha m of x, right? But looking that we have a different index here, we have m and 1, okay? Well, this inner product is going to be equal to 0 due to the orthogonality condition. And this is also going to be equal to 0. Actually, every other inner product is going to be equal to 0, excluding this one that I wrote here. Because we have that, well, we have the same index, right? We have the m here and the m here, so what we can say is that this element is different from 0. Okay? So with this, we can establish that the integral from 0 to b of x, f of x, Jn alpha m of x dx is equal to Cm, that I'm taking out of the integral, and then the integral from 0 to b x Jn alpha m of x dx. And this is squared, right? Because these functions are equal. Okay? So with this, we can say that Cm is equal to the integral from 0 to b of x, f of x, Jn alpha m x dx divided by the integral from 0 to b of x, Jn squared of alpha m x dx. So with this equation, we are able to calculate the coefficients of that infinite sum that allows us to express f in terms of a linear combination of Bessel functions. Okay? And recall that what we have here is just the inner product with respect to x of f and Jn of alpha mx. Okay? So we can say that Cm is equal to the inner product between f of x, comma, Jn of alpha mx. I mean that we are taking the inner product between an arbitrary function that we want to express in as an infinite sum and some Bessel function. Okay? And this is divided by, well, here recall that this is the definition of the norm of the function Jn of alpha mx. Recall that in vectors, when you want to know what is the norm of the vector, right? For example, the vector u, you make the dot product between u, and actually this is the norm squared, right? So you are taking the dot product between the product with itself, right? And we are considering that, well, this dot product can be seen as an inner product. Well, in this case, it's just the same. This inner product can be seen as the dot product, but now we are speaking in the context of functions. So the dot product will be this inner product, and we are making the inner product with itself. Okay, so this can be seen as the norm of Jn alpha mx squared, right? Okay, perfect. So if we take this result into the infinite sum that we defined for f, we will have that f of x is equal to the sum from I equals to 1 up to infinity of ci, right? But ci will be this thing over here, but instead of writing m, we will write I. So this will be the inner product between f of x and Jn alpha I x, like this, divided by the norm of Jn alpha I x squared, and then this all multiplies Gn alpha I x, right? Recall that these are the Bessel functions of order n. Okay, we can see this in a different way as the sum from I equals to 1 up to infinity of the integral from 0 to b of x f of x Jn alpha I x dx, and then here the integral from 0 to b of x Jn alpha I x squared dx, and then this all multiplies Gn alpha I x. Perfect, and this is the result that I wanted to get, because this expression is known as the Bessel-Fourier Series. Okay, so we will be working with this concept to explain it further, but for now we are going to finish here after giving the definition of what is the Bessel-Fourier Series. Perfect, so I hope you enjoyed the lesson, and I think that I'm going to finish here.